So start recording. Mic is good. Connection is good. All right, so this is good. So last time we started on the Dijkstra's algorithm, and I gave you an example of the Dijkstra's algorithm running in the form of a trace. So it does get very tedious, as you can see here. It does get quite tedious, but we found the shortest path. And this one was a little bit tricky because we got two paths, and it looked like the first one, the one on top, would be the shorter one, initially, and then we found that no, it's not that short, okay, because it took 31, as the length of the entire path to go from A to B and then to D. So even though we found a path, A star did not finish because there were still some elements in the set queue, and then it found the shorter path, or the shortest path in this case, which is from A to C to D, and the updating, was done correctly. So it basically, when you look at all the red arrows of the solution of running the Dijkstra's algorithm, it is telling you how to get to the closest destination from any vertex. So it's not just telling you how to get from a particular vertex to a particular destination. It tells you how to get from any vertex to the closest destination. And that's kind of the beauty of this particular algorithm, is it's not point to point. It is any point to any point, which is kind of cool. And A star doesn't do that. A star is definitely just point to point. So are we okay with this example? Are there any questions about this particular example? No questions? Okay. So did anyone do like another example on your own with like a loop, something that goes around, especially with zero distance edges? So it seems like, isn't this kind of tricky, because it doesn't matter how many times you go through in a circle, when all the edges have a zero distance, then it doesn't really change the overall length. So we can now have a quote-unquote shortest path that goes around and around and around, and then it goes to the destination, right? So what we'll do today is to kind of start on that note, and then we'll see what happens with A star when you do have a circle, when you have a what we call a loop in the graph that has a zero cost or zero distance edges, composing the entire loop. Okay, so that's what we'll do today, or at least at the beginning. And then we'll see whether we have enough time to go over the A star algorithm, or at least some of the concepts of the A star algorithm, starting with what a heuristic is. All right, so we're gonna do another example, and in this example we have we want to have a loop. Oh, wrong color. So let me switch back to smaller, a thinner line and a different color. Okay, so we have A going to B and C. B goes to C with a zero distance edge. C goes back to B in using a zero distance edge. Okay, and then we have A going to B, and let's have C going back to A. And then we have B going to vertex D. Let's see. Let's try out one example where we have two destination vertices, right? I mean, because it's supposed to work with that too. So now we have another destination vertex here, which is vertex E. So the two destination vertices, I'll use double circles to kind of make sure that we understand those are destination vertices. And then we have to associate distances of A to B, B to D, C back to A, and C to E. Okay. All right. So let's make this tricky, because everybody is going to say, oh, the shortest path from C to a destination looks like it's going to be C to E. Let's make sure that does not happen, right? So we'll make this edge, or make the distance of this one single edge here kind of expensive. Okay, it costs 20 units of whatever we are measuring. The rest we can gonna use smaller values. We'll put a 1 here, and then we'll have a 2 here, and another 2 here. Is that okay? So this is our new graph, and we want to apply Dijkstra's algorithm to this graph, and try to figure out what is going to happen, as we go through that algorithm. So are we okay so far with this? Okay. So I'm thinking about how to log this, because the way that I did it earlier, in the previous class, is really kind of clumsy and it's really kind of difficult to go through. So what I want to do this time is to use a spreadsheet to keep track of a trace. So that way it's easy to kind of scroll back and forth, to find out what's happening. I still want to display the algorithm on the left-hand side. So this way we can kind of track, which step are we doing. So we may not need to use, like a huge font size like that. So I'm going to use a smaller font size, maybe 1 step, 2 steps like that. Would that be readable to you guys? Because this way I can fit the entire algorithm on one screen, and so this way we can kind of go back and forth between the graph, the algorithm, and the trace. Is that okay so far? Okay. All right. Good. Good. And then what we'll do is to shrink this one. Okay. Oh, no. This is useless. So let's get rid of that. And we'll shrink this one a little bit so that it's only displaying that portion. And I don't really need the toolbars to be displayed, so I'm going to have my spreadsheet to overlay on top of the toolbar of this one. And then for the spreadsheet, I'm going to use LibreOffice Calc. And I think we can make this one just a little bit more narrow. Like so. And then try to fit this over here. And still show the graph itself. Okay. So I think that looks okay. As long as I can work within the confine of these windows, I think I think we can do a better job logging what's happening with all of those variables. Okay. So we got Q, which is a set. I'm going to resize the columns a little bit, just so that I will try to make everything fit on the screen. We got 1, 2, 3, 4, 5 vertices. And with each vertex, we have a few things. So we also have E prime. Okay, so we'll put E prime here. So Q and E prime can, especially E prime, that can take up a lot of space, because we are putting a bunch of 2 tuples into it. So that can take up quite a bit of space. And then we have the L values, which is the length of the known shortest path from a vertex to the closest destination at any point of the execution of the algorithm. So the way I'm going to do that is just to do an L here, and then I have A, B, C, D, E, like that. And then I'll merge some of the columns a little bit. Okay, so we have A, B, C, D like that. And then for this one, we'll merge that. So it's a OEM to merge. So now we got all the L values having their own columns. Let's see, what else do we need? I think we need to track the variable V, because in the algorithm we want to choose a particular vertex V. So I want to make it clear which ones we have chosen. So we'll put this to the left-hand side of this column. So this is going to be V. And then over here, we also want to know what is the W. So we'll have another column for W, like that. And these two definitely do not need to be too wide, because they are single vertices. Q doesn't get too big either, because Q can, at the worst, it can only be the 5 elements, right? A, B, C, D, E. So it doesn't need to be that wide. And then D is the one that's going to be taking up quite a bit of space. Okay. So we'll give it more room. Okay, all the way here. There we go. Okay. And then we use another feature of a spreadsheet. Oops, not that one. I think it's that one. Yep, it is that one. So this allows us to scroll one side of the spreadsheet without affecting the other one. I don't need to kind of do it this way anymore because I'm not handwriting anymore. Okay, so let's go ahead and do the initializations. So the initialization, which is all the way up here, is we have to initialize every destination vertex with an L value of 0. So in this case, D and E are the destinations. So those two would have L values of zeros. Is that okay? And then everything else, would have a initial L value of infinity. And that's just, because, we do not even know whether a vertex can get to one of the destination vertices. So the assumption is, okay, let's just assume that they are not even connected to a destination vertex. And as a result, the length of a shortest path is assumed to be infinite. Okay? And then we initialize E prime, that's the easy one because E prime is initially an empty set. And Q is initially all the elements that are destination vertices. So in this case, D and E are both destination vertices. So this is the initialization. So row 3 basically combined all of the initialization into one single row. Just because the initialization doesn't. I don't need to go through a loop to initialize all the L values. Doing it this way is a lot more concise. Do we have any questions about row 3 of the spreadsheet? How we put all of these initial values into the columns? It's all good? Okay, all right. So now we can kind of focus on the loop itself. So I'm going to scroll the algorithm to only look at the loop because we're done we're done with the initialization part. All right, so the first thing we need to do is to say, okay, is Q empty? Definitely not empty. It has got 2 elements. Then we get into the loop and we say, okay, we have to select a vertex from that set such that the L value is the least of all of the vertices still in Q. Okay, so you look at the L value of D and you look at the L value of E, and they are the same. They're both zeros. So in that case, it doesn't matter which one you choose. Okay, just flip a coin and say, okay, pick one of them. Okay, it doesn't really matter which one. So let's say we pick E. Okay, for no particular reason, we pick E. So that means you also have to remove it from Q because this line over here, it says whatever you pick from the set Q, you have to remove it from Q because otherwise the loop is going to be infinite. So since we are now considering a vertex E, so now we only have vertex D left in the set. Is that okay? All right, cool. And then we have to look into all the edges going into vertex E. So vertex E is here. Only one edge goes into vertex E, and that is from C. So edge CE is what I need to consider. So that will make W vertex C. And now we have to look into this conditional statement, which is basically asking, did I find a shorter path? Did I find a shorter path for vertex C? Yep, because vertex C had an initial L value of infinite, and now it is only 20. Okay, so the answer is yes, we found a better way to do it. So as a result, we update the L value of C, so it's now 20. And we also have to add vertex C into the set Q. So now the set is C and D, has C and D in it. And we also have to add the edge into E prime. So CE is now an edge in E prime. Are we good so far? Okay. So we are now done with one edge that is ending up at vertex E. Do we have any other? Nope, that's the only edge. Okay, fine, we're done. So we are now done with the for each loop. And since this is the last thing we have to do inside the while, we just basically go back to the while and ask the question again, is it empty? Nope, it is not empty. So let's pick a vertex for V. So this time we can choose between C and D. The L value of C is 20, doesn't look too attractive, but the L value of D is 0. Oh, that's better. So as a greedy algorithm, it always chooses the one that looks most promising, okay? So it's going to choose D to become local variable V in the loop. And as a result, we have to remove it from the set Q. So Q is now only having just one single element, which is C. Then we have to look into every single edge that is ending up at vertex D. So we look up vertex D, and they go like, okay, we only got one edge going into vertex D, and it's coming from B. Okay, so that makes W, vertex B. And now the question is, did I find a shorter path for B to get to a destination? You look up the L value of B at this point is infinite, which means we have not found a path at all. But now that we have this path, which consists of one single edge, hey, we got it. And the cost or the length of that one path is 1. Okay? So we update L of B to be 1. We add the edge BD into the set, okay, E prime the set. So it now has what we had before, but we also have BD in it. And we also want to make sure that we add something to Q. What are we adding to Q? B, that's right. Okay, so B, C are now in the set of Q. And we are done because there are no additional edges ending up at vertex D. So there's only one edge that we have to consider. So now we get back to the loop, the main while loop. Q is not empty, so we cannot quit yet. And we get back to the select statement, selecting a V from Q such that it has the smallest L value. So we have to choose between B and C this time. B has a L value of 1, C has an L value of 20. So B is the one that we are going to choose because, once again, we have a greedy algorithm. It just looks at, the values and go like, we'll pick the most promising one, okay? So we pick B as our next vertex to quote-unquote expand. And C is the only one left because once we choose something from the set Q, we have to remember to remove it from the set Q. And now we try to look into every incoming edges, of B, okay? All the edges that ends up at vertex B. There's only one, that's the one coming from A. So that means, we now consider A as our variable W. And the question is, well, did we just find a shorter path for vertex A to get to a destination? According to the L value of A, we haven't found a path to go to a destination yet, and that's why the L value is infinite. Okay, so but yes, okay, because if you add up, okay, so right here, if you add up the L value of V, so our V is B, L of B is 1. And then you add to it the distance of the edge that we're considering, which has a distance of 2. 1 plus 2 is 3. So the question is 3 less than the L value of A, which at this point is infinity. 3 is less than infinity. Okay, so we have the statement or the condition being true for the conditional statement. So we get into the then portion of the conditional statement. So the first thing we do is we update the L value. So the L value of A is now 3. And then there's nothing to remove because we have not recorded yet any edges from, going from A to any other vertex yet in E prime. So we are not, there's nothing to update from that perspective. But then we have to add that edge into the set of E prime, which is AB. Okay, so AB is now a new edge in the set E prime. And we also have to remember to add A into the set, into the set Q. So now the set has A and C in it. And we are done with the for each loop. Yes? Oh, right. Okay. We could have done that too. Yep. Yep. I forgot about there's another incoming edge, to vertex B. Okay, so that's a good reminder. Thank you. So we consider the other incoming edge coming from C into B. See this edge here? I forgot about it. So now we have C going to B, and we ask the same question. Did we just find a shorter way for C to get to a destination? I think so, right? Because we go through the math again. We are evaluating this conditional statement, or evaluating the condition of this conditional statement. L of V is L of B, which is 1, right? And then the distance of the edge that we are considering, it has a distance of 0. 0 plus 1 is 1, okay? But now we have to look up W, which is C, and ask, okay, what was the length of the shortest path that we have recorded up to this point? According to this, it was 20. Well, is 1 less than 20? Yes. So we just found a shorter path. So that means we got something to update now. First thing to update is the L value according to the algorithm. This order is not really important, okay? You could have, update, E prime first. But since the algorithm says, update the L value first, we'll go ahead and do that. So the L value of C is now updated to 1. And then we have to remove, so I'm going to separate these two into 2 steps, just so that it is clear what we are doing. Because the first step, according to this part here, is to remove all the edges going from vertex C to any other vertex. Doesn't matter which one, okay? So if we have an edge in E prime that goes from vertex C to something else, get rid of those edges. Well, we only got one edge like that, so we'll go ahead and remove that one, which is going from C to E. So we get rid of this edge like that. And then we have to add back the new edge, which is from C to B. And that's the function of the next statement. So now we have, this. And then, I'm just adding it after I punch in this. Oops. Click. Okay. And we are adding CB, into the set of E prime, because that's the edge that leads to the shorter path from C to a destination. So we are adding that one in. And then the last thing we have to do is to add C into the set Q, which already has it, right? But that's okay. We'll just say, okay, we're adding C into the set. Even though it's already there, I still rewrite it just so that I know that it is, there's an operation involved. I don't do that to E prime because E prime is just too long, and it's a little bit too tedious to do that. So are we good so far? Yes? Okay. So are there any other incoming edges to B? Nope. It only has 2 incoming edges, so we are done with that. So we are done with the for each loop. We go back to the while loop. Is Q empty? Nope. It has 2 elements. So let's go ahead and pick the one with the smallest L value. So we are now choosing between vertex A, which has an L value of 3, versus vertex C, which has an L value of 1. Vertex C is the one that has a smaller L value. So we choose C to be V. Okay. And then we ask the question, oh, okay. I almost forgot about updating Q, because every time you choose something from Q, you have to remove it from Q. Then we ask the questions. What are the incoming edges of C? C only has 1 incoming edge coming from B. Okay, so we put B here. And then we ask the question, do we need to update anything? So we go through this condition here. So this time we are asking L of C, which is 1, plus the edge that we're considering, which is also 1. Is that less than L of W? W is B, which also has an L value of 1. In other words, we're asking, is 1 less than 1? The answer is no, right? So that's why there's nothing to do, okay? This is why infinite loops, loops even with distances of 0, does not bother the Dijkstra's algorithm, because you're maintaining the cost, but you're not finding a lower cost. And as long as you're not finding a lower cost, there's nothing to update. We are not putting vertex B back into Q, okay? Is that okay? This is also why you are not supposed to have distances of negative value, because if you have edges of negative values and you have a loop, that means going through that loop more times is reducing the distance to to a destination. It doesn't make sense. Okay, I cannot find real life problems where that is the case. The more you do, the more time or resources you're saving. If someone claims that there's such a thing, the first word that comes up in my mind is scam. So nothing to update here, which is good. Okay, so now we are done with the for each loop. We get back to the main while loop. Q is not empty. It has got one element at this point. So, well, I don't have to choose now, because if I only have one element, that has to be the one that I'm going to consider. So now we have to look into all the incoming edges of A. It's only got one. Okay, it's coming in from C. So we go through the same calculation again, using this part here with the conditional statement. So we look at L of A. Okay, L of A is 3. We look at the cost of that edge. Okay, that edge has a distance of 2. 3 plus 2 is 5. Okay, so we are looking at 5 here, which is the left-hand side of the less than. Then we look at L of W. L of W is L of C. L of C is 1. Is 5 less than 1? No. So that means there's nothing to do, nothing to update, because we are not going into the then portion of the conditional statement. Then we go back to the main while loop. The main while loop says, well, is Q not empty? It is not true that Q is not empty, because it is empty. So that means we're getting out of the loop. We're done. Is that okay? So, okay, now that we are done, what does it mean? What does it mean when we are done? What are the edges? Well, we only got 3 edges left in E prime, and that represents the solution graph. Okay, what does it look like? Because when we look at the text version, sometimes it doesn't really give us as good of an idea of what it looks like. So what we'll do is I'm going to scroll this one all the way up so I can still see it when I pop this window open. And then we're going to choose a different color. Okay, we'll use red again. So I'm just going to highlight the edges that are in the solution graph, right? So BD is in it. Okay, so BD. So this is in the solution. AB is in it. Okay, so this is in the solution. And CB is also in it. CB. So this 0 distance edge is also in it. All right. Huh? Say that one more time. E also is one of the destinations, but nobody is going to E. Now E is okay. I mean, if you ask the question, what is the shortest path to go to the destination from the perspective of E, the answer is stay put, because you're already sitting on a destination. But it's not going to be this. There's no edge to display in that case, because you're already sitting on the destination. So the edges, or the red arrows, are indicating if you're in vertex C, the shortest path to a destination is to go to B first and then go to D. So is it like any destination? Yeah, go to any destination. Think of the little boy and bathrooms. So E is just way too expensive to even consider if it's any destination. That is correct. Yep. So once again, we have a graph that shows you how to go from one vertex to the closest destination, but it applies to the entire graph. Yep. Uh-huh. Yes. Yes. So it only shows you one shortest path. So if you have two paths that are equal in terms of length, it will only figure out one. It will only display one. Because in this case, you can argue and say that I can go A, B, D, I can go A, B, C, B, D, I can go A, B, C, 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 B, B, D, right? I mean, but those paths are irrelevant because I just need one. I just need one shortest path. Yep.
If the cost of going from D to E was 0, would the program halt or the algorithm halt at D and never go to E?
Okay, so if C to E, if this was 0,
If D to E was 0,
if this is 0,
right, would the program halt at just staying at D, or would it actually end up going to E as well?
okay, so
Would
let's
that be a solution?
let's think about it. Okay. So let me modify the graph first, and I'm going to use a different color, because we are considering a different graph now. Okay, so we're going to use gray. Yeah, gray is good. So you're asking, what if we have a edge going here, and it has a cost of 0, right? Okay. So what's going to happen is, um, it is not going to be helpful to us because remember we start with these two, right? And then we go backwards. So when E goes backward to D, it's like, okay, did we find a shorter path for D to get to a destination? The answer is no, because D already has the length of the shortest path to a destination being 0. 0 is not less than 0. So there's nothing to update. The rest of the algorithm will run exactly the same way as we did this without the gray arrow.
So even if the cost of going to E was 0, there's no chance that the algorithm would say that you should go to it.
And it has to do with the edge going into E has a cost of 20 here. If you change this 20 to something a lot, if you change it to something a lot less, then C would actually go there. Because right now, the shortest path of C to go to a destination is 1. So that means if you turn this into a 1, then C will probably pick this path instead of the other one. But it's a tie, so that means it has to do with when you choose something, which one are you going to choose. So by randomizing that portion, sometimes it will choose the direct edge from C to E. If you change CE, the distance of CE to 1, sometimes it will do it. Sometimes it will still keep doing it this way because it's probabilistic now. So any other questions? Yep. You really want to what? You change the setup so that D is not considered a destination. Mm-hmm. It will find the shortest path to one destination. It does not find all paths to all destinations. It finds the shortest path from any vertex to a destination. And all destinations are considered quote unquote equal. Just remember that little kid and bathrooms. Does it matter which bathroom you want to go to? The answer is no. Just get me to a bathroom. Hmm? That doesn't count because now you're assigning weights to bathrooms.
You wouldn't know unless you were already there.
Well, somebody could be there already and come back and let you know, right? I have been to enough camping, trips. Yep. And that function changes every day. Depends a lot on the other campers. Okay, so do we have any other questions about this particular example? No questions? Okay. So if you look at the solution graph, do you think that we can have two vertices or two edges going into one single vertex in the solution? I mean, it does happen, right? B is a good example. The second question, do you think it's possible to have two outgoing edges from the same vertex? And if that is not possible, why is it not possible? But what if they're the same? Then they're the same length, right? It'll be random. Well, if you look at the algorithm, it can be explained by these two statements. Before you put an edge in, you remove all of the outgoing edges. So that means at any time, you can have at the most one outgoing edge from any vertex in E prime. Oh, okay. If that is the case, don't you think there's a special property in the solution? Regardless of what kind of graph you're dealing with, there's a special property in the solution. It's not necessarily a tree, but it will be tree or trees. So it would be a forest. And I'm not kidding. Some people are saying like, "Oh, you must be kidding, right? I mean, having multiple trees is a forest." No, that's actually a technical term in computer science. When you have multiple trees, it is called a forest. Yep, learn something new. So the solution graph of Dijkstra's algorithm, at least the one that I use in this class, is guaranteed to be a forest. Yep.
Would that happen if you had like two destinations and the E prime ended up splitting it like into
Yep.
two trees?
You can come up with examples, pretty quickly with that one. So I can give you an example that will clearly be a forest. Okay. Where's my default color? I guess we can just click that. Okay. It's still gray, is it? Yep, it's still selecting gray. Okay, that should put it into black. Yep. So we got vertex A, we got vertex B, vertex C, and vertex D. This is my original graph. It doesn't even matter what the distance is, right? So your solution graph has to be, there's no other way. So your solution graph has to be AB and CD. This is a forest. Because AB is a tree, and then CD is a tree as well. So you have two trees. Yep.
So what happens if you have like the graph before, but you just have a third, like an extra node that you make the destination instead? Does it just give an empty E prime?
Okay, let me go back to that one and see if I can capture what you said.
Just like add a new node, don't connect it to anything, and make that the new destination. You'll just end up with like empty E prime.
Oh, being the only destination? Okay, yeah, so you have an empty graph.
Okay.
Yep. Okay, so we can look into that. So instead of kind of using a conjecture, we can actually just work it out. Okay, so let's just say that your graph is really simple. You have vertex A, and then you have vertex B, and there are no edges. Okay, so vertex B is fine because it is a destination itself, so it's good. But vertex A has no path to a destination. So what's going to happen with the algorithm? Yep.
The cost to get from vertex A to B is still going to be infinite.
Yep. No, the cost, the L value of A will still be infinite.
Yeah.
It doesn't know about B. It just says, okay, the length of the shortest path of A to a destination is infinite, which means it is not reachable. Yep. But if you can actually run the algorithm through your head, kind of really quick because there are only two vertices, involved here. So the initialization is B has an initial L value of 0, right? Because it's a destination. And then A has an initial L value of infinity because that's how we initialize everything. Q is initialized to just B itself, right? So when we run the algorithm, we remove B from Q. Q now becomes empty. Then we look for all the incoming edges to B, which there's none, right? So that means there's nothing to do inside the for each loop because there are no edges going into vertex B. But at this point, Q is already empty. So when we go back to evaluate, is Q empty? The answer is yes, it is empty, and we get out of the algorithm. So we end up with the L value of A being infinity, the L value of B being 0, and E prime is empty because E prime was initialized to be empty, an empty set to begin with, and we couldn't get into the if statement at all because the for each has nothing to do. So that's what it's going to end up with. Is that okay? All right. Any other questions regarding Dijkstra's algorithm? Yep.
A graph question. So the only thing that's like distinguishing what, like if we have a graph that's not completely connected, the only thing that's distinguishing whether we're talking about two graphs and a single graph is like what we formally say we're talking about, right?
Yeah.
Because you
Yep.
could potentially have a graph that's like technically two graphs.
Right. There's no connectivity between certain vertices. Right. Yep. That is true. So any other questions? So we're good with Dijkstra's algorithm. Okay. So Dijkstra's algorithm is also classified as what we call a breadth-first search algorithm. So one way to envision a breadth-first search algorithm is basically it has no preference of which direction to explore. It's just kind of expanding from the destinations in this case outward based on the distances to the destinations. Okay, so if you want a picture in your mind to remind you what breadth first search is like, so you can kind of imagine this. Okay, you can kind of imagine. Let me see if I can find something that has a picture in it, to make it easier to envision. When I was a kid, there were commercials that inspired this particular analogy, but I'm not sure whether I can still find those online. So I'm going to look up cockroach, maze, and pesticide, or bug spray. Huh? Okay. So let's go to images. Because if I can find the image, that really will help to make that picture. Is anyone squirmish of cockroaches? Okay, I'm sorry. Okay, I don't think they have any pictures. Okay, that's fine. Okay, so use your imagination then. So imagine that you have a maze. Okay, has anyone gone to the micro mouse competitions at UC Davis like a long time ago? No. Okay. So imagine that you have a maze. Okay, and the whole thing is encased in clear plastic. Okay, and there are cells, right? So let's say the maze is kind of like rectangular or squarish. Okay, so you have and then we glue a cockroach in every single cell. Okay, so every single cell has a cockroach, and then at several cells, we have these pesticide or bombs or whatever. So it will start to spread pesticide. Okay, a gas that will kill the cockroaches. Okay, so now what you need to think about is what is the order of the cockroaches dying. So the cockroach who is in the square where I start distributing the toxic gas, is going to be the first one to die, right? Who's the second to die? The adjacent cells, right? So that's basically what breadth first search looks like. Okay, and that's what Q is. Q is basically the boundary of who is going to die next. Is that okay? That's breadth first search, okay? Because the spreading of the gas is omnidirectional. It does not. There's no wind to blow it one way or another. There are no fans within the maze, so there's no preferred direction. Like a cockroach cannot, kind of like just look at the other cockroach and go like, "I'm upwind," or there's no such thing. Okay, it's going to spread, in all directions. Okay. So that's really kind of good from one perspective, but it's also not so useful in other perspectives. Okay, so let me give you an example. Okay, and this time we'll go back to Google Maps for that example, and we'll zoom out. Oh, that's too much. Okay, this is good. Okay, this zoom level is good. So let's just say that I'm in Sacramento right now, and I want to find the shortest path to Fisherman's Wharf in San Francisco. That's what I want to do. So breadth first search is, let's see, no, the other way around. Take it back. The other way around. I'm in San Francisco, okay, and I want to figure out how to get to downtown Sacramento. That's what I want to do. Okay, so Sacramento is the destination. So according to the Dijkstra's algorithm, we start with the destination, we expand out, right? So we start with Sacramento, we expand, so then we'll start to include Woodland, we'll start to include Elk Grove, okay, along with Davis and Dixon and so on and so forth. Now only Davis and Dixon are on that route, right? But breadth first search has no preference direction because it all has to do with how far is that place away from the destination. Direction plays no role into, should we expand that node? Nope, doesn't care, okay? So we'll keep going in this direction and keep going in the opposite direction. So in one direction, the algorithm will eventually reach Vacaville, but it will also in the other direction reach El Dorado Hill. Then it goes like, wait, El Dorado Hills, that's way off. That's the opposite direction of going to San Francisco. Well, it doesn't care. It keeps expanding in all directions, okay? So when it is all done, if all you really want to know is how do I go from San Francisco to Sacramento downtown, by the time it gets here and figure out, oh, the shortest path from Fisherman's Wharf to Sacramento is blah, 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 it would also have found, okay, all the shortest paths from everything around this perimeter. Just draw a big circle around Sacramento where it touches, San Francisco. It would have found the shortest path from every city, every town within that huge circle, which is really cool if that is what you want. But if the only thing you want is, I just want to go from San Francisco to Sacramento, then you might have just wasted a lot of resources on a lot of computation that you do not actually have to go through. Is that okay? So A star is here to fix that problem. So A star by design is a point-to-point type of algorithm. Tell me where you are, tell me where you want to be, and I'll find you the shortest path. And it is directional. Okay? What do I mean by directional? It has a quote unquote a sense of direction through the use of what we call a heuristic. Okay? So let me switch back to the notes because there is a kind of short description of what a heuristic is. So we are moving on to the A star algorithm. And don't ask me why it's called the A star algorithm. I have no idea why it's called A star. But there's a heuristic. So the description of the heuristic is in the second paragraph. The heuristic function, okay, so the first part is this part here. So this describes, what is the heuristic function as far as the domain is concerned and as far as the codomain is concerned. The domain is the Cartesian product of vertex and vertex. In other words, Give me two vertices, okay? And the codomain is the real numbers, but it's not including the negative real numbers. So it's only including the non-negative real numbers, 0 and up, okay? So look at this and go like, well, doesn't the D function look kind of like that? You're right, the D function kind of looks like that too. But the meaning is different. The meaning of the D function is literally, what is the distance of this edge going from this vertex to that vertex? That is the function of the D function. Okay, that's the purpose of the D function. The heuristic function is different. So when you look at the heuristic function, let's say we are looking at h of VW. Okay, it's really just an estimate. It's asking the function and say, give me an estimate of how far V is away from W. It's just an estimate. Okay. Then you go like, well, if I can give you an estimate, I might as well just give you the answer, the exact length of the shortest path. Well, to compute the exact length of the shortest path is computationally, heavy duty, okay? But to give you an estimate, that can be very quick to compute. Okay? So that's the premise of using a heuristic. We also need a heuristic, which is an estimating function, to be admissible. Admissible means that if L is the actual length of the shortest path from one vertex to another vertex, then we need all of the h values to be less than or equal to the L value. In other words, your estimation cannot overestimate. You can underestimate, but you cannot overestimate. And that makes it, quote unquote, admissible. It's just a term, okay? Admissible means it is underestimating, or at least not overestimating. Okay? So let's go back to the map. So if I use the map and go like, okay, so what kind of heuristic should we use when we are using, when in the case of a map? In other words, if I ask, so let's say we are looking at Concord and Sacramento. Okay, I'm asking you, give me a quick and easy estimate of what is the distance between those two. You're actually interested in your driving distance, but give me an underestimate or non-overestimate of how far these two places are. What would be one way to do it? Yep. Yep. Straight line, right? So all you do is to say, okay, if I draw a straight line from Concord to Sacramento, how many miles are we talking about? That is guaranteed to be an underestimate, right? Or at least not an overestimate. Yep.
But that's assuming you can move diagonally, right? Like, what if you can only move
It's okay to make that assumption that you can only move diagonal, because that still guarantees that your estimate is not going to be an overestimate. Is that making any sense? So even if you can drive, only east, west, and south, north, it will still be okay to use a diagonal line as an estimate, because you just need your estimate to give you an idea of, okay, I just need a rough idea of how far they are. Okay? So do we have any questions about the properties of a heuristic, which is just an estimate that is guaranteed not to overestimate? Yep.
So the A star doesn't specify a specific. It doesn't give a specific one. It just says any that's an underestimate.
Anything that is not overestimating can be used as a heuristic.
So you can just always estimate 0.
Yep, you can always say h blah blah is 0. Then it becomes almost the same thing as Dijkstra's algorithm, because you don't have a preference of direction anymore, and it becomes just expanding, just like Dijkstra's algorithm. Yep.
To make sure I'm understanding this right, this underestimate is something that we're going to use for the algorithm, not the answer that the algorithm is going to.
That is correct. You have to first provide a heuristic function in order for A star to work. But as you said, you can always use 0, map everything to 0 as your heuristic function. And A star will work, but you might as well just use Dijkstra's algorithm in that case because you're not gaining anything from using the A star algorithm. Yep.
You were trying to get somewhere like in 3D space
Uh-huh.
with the search algorithm, and you use the distance formula. But let's say one route is just a flat line straight to your destination, and another one is like a really bumpy line.
Uh-huh.
That would be more expensive, but they would have the same distance.
That is correct.
So then, how would you differentiate between which one's better?
As you, so you can, okay, you can even have it, you can have your heuristic function to be tricky. In other words, something that's closer, you make the heuristic function exactly the same as the original distance, and something that's really far away, you make the heuristic function, artificially small. In other words, you can design a heuristic function to try to trick the A star algorithm to go where it's not supposed to. But as long as your heuristic function is not overestimating, you can try your best to trick the A star algorithm. It will still find the shortest path in the end, as long as the heuristic function is not overestimating. So you're correct. Okay, you can make a heuristic function that is not entirely accurate, but that's the whole idea. Is we don't need it to be exact, because if I want it to be exact, I might as well just find the shortest path, right? So do we have any questions about what a heuristic function is and what is the necessary property of a heuristic function? No questions about that? Okay. All right, so given that we have a heuristic function, I'm just going to go through the algorithm first, and then we'll do an example. So once again, the graph that we are trying to work on is G, which is a two-tuple. V is V is the set of all the vertices. E is the set of all the edges. We have the same distance function. Distance function only apply to edges, so it maps n edge to a non-negative real value. Now in this case, you can only have one start vertex. In other words, where are we starting? Are we starting in San Francisco? Are we starting in Sacramento? Pick one vertex as your start vertex. Okay. So this makes it quite different, in terms of how we set it up compared to Dijkstra's algorithm. You can only have one vertex as the destination, which is also a restriction that was not in Dijkstra's algorithm. So with A star, you have to pick a starting point and you have to pick a destination. So are we good with that? Okay. So you have to tell the algorithm that. And then you have to choose a particular heuristic function, and you have to make sure that HVW is not overestimating the actual length of the shortest path between vertex V and vertex W. Okay? So all of these are inputs into the algorithm. Give me the graph, give me the start vertex, give me the destination vertex, give me the heuristic function. Okay, so those are all the necessary ingredients to get the algorithm started. So the initialization, of the heuristic function, there are different symbols here. Okay, so we got a function called G, we got a function called F, and the function G, or G of V, is basically you're asking what is the length of an actual path from vertex V, from vertex S, the start vertex, to vertex V. Okay, so that's what G of V is. F of V, on the other hand, is the estimation. What kind of estimation are we talking about? It's the estimation of the length of the shortest path starting from vertex S through vertex V to vertex X, which is our destination. Is that okay? Okay, I think a picture can help. All right, so we'll draw a picture here. So here's vertex S, which is your start vertex. Here's vertex X, which is your destination vertex. Okay, and here's vertex V, which is the one that we are asking questions about. If you have found a particular path, okay, from S to V, G of V is the actual length of the shortest one of those paths. So G of V is the length of the shortest known path from the start vertex to vertex V, which is the one that we are considering at this point. Is that okay? Are we good? Okay. What about the F value? The F value includes the estimation here. So if G is measuring this, then F of V is measuring this. Is measuring from here to here, and then from there to there. That's F of V. So F of V is really simple. All it is G of V plus the heuristic of V to W, V to X. So let me finish this. It's basically G of V plus the heuristic of going from V to X. So these two are particularly useful in the algorithm. I just want to make sure that we understand what is the G function and what is the F function as we discuss the algorithm. So are we good so far? Okay. So if I switch back to the initialization code, all it says is for anything that is not the start vertex, we initialize both the G and the F value to infinity. In other words, we are assuming that, well, until I know there is a path, we'll assume the length of the path, from the start vertex to V is not known. Okay, so the length of that path is infinite, and because I don't know whether I can get to V from the start vertex, so if you ask me how far is it to go from the start vertex through V to X, I'm going to have to say that that is also infinite. So are we okay so far with this initialization? Yes? Okay. What if V is S? What if we are talking about the start vertex? Well, then it's easy. Because the shortest path from the start vertex to itself is 0. Kind of makes sense, right? What about the estimated distance of the start vertex going through itself to the destination? Well, isn't it really just the heuristic function applied to the start vertex and the destination vertex? So that's why we initialize the G and the F values like this. Do we have any questions at this point about the initialization of the F and the G values? Nope. Okay. Then we move on to the initialization of O, which is kind of doing the job of Q, but not exactly the same. So the initialization of of O, the set O, is really just starting with the start vertex. And we are guaranteed to only have one single start vertex in the case of A star. So this is the big difference between Dijkstra's algorithm and the A star algorithm. The Dijkstra's algorithm starts with all the destination vertices in Q, but the A star algorithm starts with the single start vertex in O. Is that okay? So I just want to point out the main differences between the two algorithms as we go through the algorithm. So are we good so far? Are we ready for the next line, which looks kind of cumbersome and kind of like, ooh, what is that? Okay, so we'll address this thing here. So instead of saying as long as O is not empty, we continue with the loop, now we attach a conjunction and say something about that. Okay? And I think the way I set this up is actually wrong. I think this V is supposed to be O. Okay? So I'll fix that later. Now, what if you cross out the conjunction part? It will still work. But you might be doing some unnecessary work if you cross out the conjunction. So we'll talk about that later. But this is the condition to stay in the loop. What this is saying is if there are candidates on, if there are still candidates of a path that is shorter than what I have found so far, continue to explore. So it's basically asking, so now you have to think about when can we guarantee that there are no further shortest path possible at this point? So when can you draw that conclusion? So the next line looks a little bit like the one that we had in Dijkstra's algorithm, except this one says, let's pick a vertex C in O such that for everything in O, f of C is less than or equal to f of W. Haven't we seen something like that when we select V from the set Q with the Dijkstra's algorithm? Yep, it's kind of the same thing. It is also a greedy algorithm. So A star is also greedy because it's looking for the most promising candidate. Tell me again, what is the F value? What is the meaning of the F value? Not the definition, but what is the meaning? It's, it's the estimated length of the path from start to destination through a particular vertex, right? So now I'm asking, okay, let's go through every single one of the elements in O and tell me which one looks the most promising. Okay, if I start with a start vertex, go through this vertex, go to the destination, this is the least of all the estimates. Okay, so once again, I'm looking for the most promising candidate of all the choices that I have in the set O. Okay, once I have chosen that, this looks familiar too. Once we have picked out something from the set, let's remove it from the set. Okay, because we don't want to keep it in the set, then we will get into an infinite loop. The next one, which is a for each loop, also looks kind of familiar, except the direction is opposite. So instead of looking into incoming edges into the vertex that we have already selected, we're looking at the outgoing edges. So now we start with C and ask, where can I go directly from C through edges? Okay, so N is the other vertex on the edge, and we can go from C to N in this case. So C is kind of like doing the job of V in the previous algorithm, and then N is kind of doing the job of W in the previous algorithm, except the direction is opposite. Okay, so instead of looking into incoming edges to V, we are looking at outgoing edges from C. Are we kind of good so far? You can see the two algorithms are very similar in many ways. Then we compute a certain value. Oh, this looks kind of familiar too. I mean, before we have the L value plus the distance of the edge. This time we have the G value plus the distance of the edge. Well, remember, the L value is the length of the shortest path to the destination. The G value is the length of the shortest path from the starting point or the start vertex to this vertex. So yes, they are very much related. Okay? And then we just add the distance of the edge. In other words, I'm now computing, if I start from the start vertex and I go through vertex C to vertex N, okay? I know we can get to vertex N because there's an edge here. The question is, well, did I just find a shorter way to get from the start vertex to vertex N? That's the question. Did I find a shorter way? And that's why we have this condition here. We compare T, which is the length of the path going from the start vertex through C to N, and we're comparing that to the length of the known shortest path to N at this point from the start vertex. We do the comparison and say, well, did I find something that's shorter? If I do not find anything that's shorter, okay, fine, nothing to do. But if I do find a shorter path, what do we do? Well, that looks kind of familiar. We add vertex N to O in this case, because we have just updated, we are going to update some of the values of vertex N. So anything that N itself connects to may potentially be impacted by this discovery. So I'm putting N into the set O so that we can expand and explore those later on. Is that okay? The next line is a little bit different. Instead of keeping track of E prime, I decide to choose to use the previous function so that I'm keeping track the previous of N is C in this case. So it's kind of doing the same thing as E prime, but it's a different way of representing it. Okay. So is that okay? Does everybody understand what is prev? The previous of vertex N is C. That's what it's trying to remember. Okay. But because of the use of a function, I don't have to erase anything anymore because a function can only maintain um, it's for each element of the domain, it can only have one thing it can map to in the codomain. So that kind of guarantees that I don't have to erase anything first. Next one, g of n is now updated to t because I just found a shorter path. I just found a shorter path from the start vertex to vertex n, and t is the value of that length, so I just updated that way. Is that okay? And then the f value is also updated because the g value is updated, so I need to update the f value as well. So by definition, the f value is really just the g value plus the heuristic of n going to vertex x. So I just update the f value this way. Okay? And then it's done. The conditional statement is done, and then the for each loop is done, and then the while loop is also done at this point. I mean, just from the structural perspective, I'm not tracing anything at this point. So do we have any questions about the algorithm? It looks really a lot like the Dijkstra's algorithm. How many people are taking 430 this semester or have taken 430 already? Okay, so in 430, I think they talked about Dijkstra's algorithm too. No,
We haven't yet.
not yet. Huh?
Fires last semester.
Uh huh.
The people that were in SAPS Fires last semester skipped that whole thing.
Yeah.
Oh. Okay, that's good. That means you won't be confused. Because in some previous semesters, I would talk about Dijkstra's algorithm, and then Subsidiary will talk about Dijkstra's algorithm as well. But his version in his class is different from mine. He doesn't work with multiple destinations, and I do work with multiple destinations. He starts with a start vertex and not the destination vertex, and I start with the destination vertices. I mean, it still works out the same way. They're both correct. Mine is just slightly more flexible, and it finds all the solutions all at the same time. But then people get confused. It's like, oh, but which version should I use in this test? And my answer is quite easy. If you're in my class, use my version. When you're in his class, use his version. Okay, that's basically the bottom line. Okay. So, but because we are not keeping track of E prime, we have one last step to do. In other words, how do we express the solution graph? So in this case, the solution graph itself, it has a suffix. So the suffix indicates that this is the solution graph of starting with vertex S and ending with vertex X, because we no longer have a universal solution graph in Dijkstra's algorithm. Is that part okay? I just want to point out the main differences between the two. Dijkstra's algorithm is a universal solution, which means the solution graph that we end up with in Dijkstra's algorithm finds the shortest path of every single vertex to a destination. It doesn't matter where you are, I will tell you where you need to go to get to the closest destination. So it's a universal solution. But in the A-star algorithm, the solution graph is only good, it's only useful if you are standing on the start vertex and you want to go to a particular destination vertex X. It does not help you if you're somewhere else. Okay? So that's why the solution graph itself has this notation of GSX. SX means in the suffix because it is specific to those two vertices, one being the starting point, one being the destination. Yes?
Are you saying with Dijkstra's, you go through the computation method to generate
Yep.
all the possible paths from one destination to the ones that you don't care about?
It generates the solution of all the vertices, not just the destinations.
And then for A star, you'll just generate just the one solution graph.
It's only useful for that. Yep. Yep. So I define this to be V. It has the same vertices, but the edges are different. Okay. So the edges is represented by ESX. Sounds like an Acura. I don't think there's an Acura of ESX yet, but there might be one in the future. But ESX, stands for the edge set. Okay. When you want to go from vertex S to vertex X, okay? And the way it is constructed is really just described here. For every W in V, if pref W is V, then you also want VW to be in that edge set. That's all we do. Okay, we just look at the previous function, and then we ask, okay, who is whose previous, and then we create those edges along the way. So do we have any questions about Dijkstra's algorithm as far as the structure of the code is concerned? Are there any questions relating or not relating or differentiating Dijkstra's algorithm from the A-star algorithm? No questions? Now I can also tell you one interesting property of the A-star algorithm as compared to Dijkstra's algorithm. Dijkstra's algorithm cannot really finish unless it is finished. Okay, there's no partial answer you can expect out of Dijkstra's algorithm. If you look at this A-star algorithm, it's kind of the same way until it runs to completion. You cannot decide what to do next. Okay, but there are variations of the A-star algorithm, which we call, I cannot remember the name. It's a successive approximation kind of approach. Okay, so this is the scenario. Okay, the scenario is you are a robot. You're dealing with a real-time problem. Okay, you need to solve a problem before a hard deadline. It can be something like, has anyone seen prune sorting machines? No? Prune sorting machines. So after the farmers harvest all the prunes in an orchard, they need to be sorted. Okay, the ones that are deformed, they send it to like a prune juice factory, and the ones that look nice and have the right shape and the right size, you can sell those actually as prunes, right? So there's a machine to do it. So the machine does it in a very interesting way. There's a hopper. It shoots each prune over a certain area in midair. Okay, and then there is a system of cameras looking at the prune from different angles. It runs through some kind of algorithm, possibly neural net these days, and it has to come up with a decision of, is that good or not? Can we sell this, or are we going to juice it? Okay, if we're going to sell it, then it continues its trajectory into a collector to collect all the prunes that you can actually sell on the market. If it fails that test, then there's a mechanism to actuate a puffer. It's compressed air. Okay, so the compressed air will basically alter the path of the prune in midair into another bin, where it is going to a juicer, and we just extract the juice. Okay, so it's a real-time problem because there's only so much time in midair that you can make that decision. Should I turn on that compressed air jet, okay, to push the prune, or should I just let it fall into the bin? Is that okay? So this is called a real-time problem. Okay, it's a real-time application where you have a hard, deadline that you cannot miss. Okay. Now, nothing too bad is going to happen in this case, but if you think about a robot arm that can grip something that is falling, and that something that's falling can potentially be very damaging or very heavy, then someone can get killed, if you don't, close the grip fast enough. Okay, so there are applications where you have to make a decision within a certain amount of time. Neither Dijkstra's algorithm nor the A-star algorithm can guarantee that, I can get it done within a certain amount of time, because it all depends on how many edges you have, what kind of heuristic function you choose to use, blah, 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 blah. So there's no actual easy way to tell how fast you can make a decision. So here comes another algorithm that is called a successive approximation. So the way it does it is it makes use of the heuristic function, and it will just deepen the search when it has time. So if you're really short of time, it will only have enough time to explore one edge from the start vertex, and the rest are estimated using the heuristic function. But it will still be able to tell you, yeah, go this way, okay? Because according to the very coarse estimation, that seems to be the best way to go. It will make a decision. May not be the best decision, it will make a decision, okay? But let's just say that you have enough time, okay? You go through, you expand the boundary by one edge, you find one solution, but it's not yet time to make that decision to actuate something in real time. You go like, okay, let's go for a depth of 2. So now you explore 2 edges, and then you use the heuristic function for the rest. And that will give you a slightly more informed decision, right? Let's say you have even more time. Then you go for a depth of 3, a depth of 4, a depth of 5. Let's say by the time you get to a depth of 5, time's up, make a decision. Then you can only rely on the search based on the depth of 4 and heuristic function. Whatever seemed to be the best option with that iteration, choose that one. So you will still be able to make a decision, even though it may not be the most optimal decision. And the modified version of A star can do that because of the heuristic function. So if you guys are interested, I can talk more about that particular algorithm. Just kind of talk about it. I'm not going to quiz you on it. But it has very interesting properties and applications. All right, I'll see you guys on next Monday. Have a nice weekend. Huh? Yeah, I will go through an example with A star. I can use the same examples, I just have to give it a heuristic function, right? Yep.